Yesterday we had Matt Jackson, who's an economist, and today, in the spirit of the diversity of the organization, we have a sociologist speaking, Duncan Watts. He told me actually he's an expert in organization. He actually taught theory of organizations, including work by Coase, North, Williamson, and Gibbons in the sociology department at Columbia when he was here. He's currently a principal researcher at Microsoft Research at the New York City lab, and the A.D. White Professor at Large at Cornell. And prior to joining Microsoft in 2012, he was from 2000 to 2007 professor of sociology at Columbia, and then a principal research scientist at Yahoo, where he directed the Human Social Dynamics group. His research on social networks and collective dynamics has appeared in a wide range of journals. He was awarded the 2009 German Physical Society Young Scientist Award for Socio and Ecophysics, whatever that is. The 2013 Lagrange CRT Foundation Prize for Complexity Science, whatever that is. And the 2004 Everett Rogers Prize. He's widely published. He has about 73,000 citations on Google Scholar. And his books, and he said he basically encouraged all of you to go over to the bookstore right afterwards and purchase one of Small Worlds, The Dynamics of Networks Between Order and Randomness, 6 Degrees, The Science of a Connected Age, and Everything is Obvious Once You Know the Answer. So I think it's extremely impressive for such a young scholar to not only be well-published, but also to write so many interesting and important books. And as I said, he would appreciate more sales. Today, he will discuss computational social science, exciting progress and future challenges. And this is an important area for understanding institutions and organizations in the modern world. Please welcome Duncan Watts. Thanks.
Anyway, it's great to be here. Thank you for making it out on a Saturday morning. So I want to talk about computational social science, and I'll try to explain what I mean by that. But first, I want to start by saying what I think is interesting about social science. And I started off life as a physicist, and my PhD is in engineering, and so I kind of came to sociology rather late in my career. So this is just sort of a very personal perspective on what I think of as interesting about the social sciences. And the way I think of it is that in the social sciences we are essentially interested in collective phenomena. We talk about things like families and firms and markets and political parties as if they are actors that have intentions and beliefs and make decisions and so on. But of course we know that that's really a convenient fiction, that really all of these actors are agglomerations of individual people who are the ones who actually have the beliefs and intentions and make decisions and so on. And somehow these people are interacting with each other in complicated ways and producing these emergent phenomena that we refer to in social science. And so this is a problem that in sociology is called the micro-macro problem, and in other parts of science is called emergence, where we are interested in this mysterious process about how we go from the level of individual people up to social actors and forces. And of course, this is a very difficult problem from an empirical point of view. And so, sociologists have been talking about this for, at least 100 years, but we haven't made a tremendous amount of progress in this area. Largely, I think, because of the empirical challenges. And it's very easy to see why this might be problematic. If you think about a social network of millions of people, the amount of data that you would have to collect just to observe who is talking to whom about what over an extended period of time is enormous. And if you care about cause and effect, you may also want to run some sort of experiment, and doing experiments at that scale is even more difficult and often impossible. So if you think about, just in very basic terms, the scientific method where you propose your hypothesis and then you devise an experiment to test your hypothesis, if you sort of can't do the second part of the scientific method, it's very difficult to make progress. And so, especially in sociology, but I think probably it's also true in economics, we have lots and lots of theories about how the world might work, and we are relatively, we have a great deal of difficulty in deciding among these theories or rejecting them. And so what is so exciting for me and my colleagues working in this field is that over the last couple of decades, we're starting to see the sort of some of these historical constraints lift. That for the first time, really in history, we are able to generate data that is sort of at least on the scale and granularity of the phenomenon that we are theorizing about. And so everybody talks about big data these days, and I think mostly when they're talking about big data, what they mean is all of this data that's been generated often by commercial companies like the place that I work at now, Microsoft, where millions or hundreds of millions or possibly even billions of people are searching for things, they are sending emails to each other, they are interacting via social media, they are purchasing things via e-commerce sites, they are increasingly talking to bots and AI agents. And in the course of going about these everyday activities, they're generating an enormous amount of digital data that people like me can sift through afterwards to try to answer questions that are of interest to social scientists. A lesser remarked upon, but I think also very important element of what's been happening over the last couple of decades is that the web is also transforming our ability to do experiments. And some of those experiments are much like the traditional psychology or more recently behavioral economics experiments that have been conducted in labs and universities like this one for decades. And some of them are more like field experiments that are where you have some sort of randomized treatment applied in the wild. And so I think if you put all of these things together, you get what I would refer to as computational social science, this sort of emerging intersection of the social sciences and the computational sciences that is becoming increasingly popular. So that's sort of very roughly what I mean by computational social science, and I'll try to illustrate that throughout the rest of the talk just really by examples. And I want to focus on two types of examples. One is more of the big data sort, where we have data from somewhere and then we try to make sense of it and use it to evaluate theories that we have, in this case about social contagion. And then the second type of data that I want to talk about is what you might think of as small data, where you are designing some experiment in a lab and you're trying to identify cause and effect. And in that case, you're really sort of not dealing with billions of people, you're dealing with maybe dozens of people, so the numbers themselves are not large, but there are other advantages that we get from this virtual setting. And so I want to emphasize that the questions here, and this is really where the social science part of computational social science is important, these questions are not new questions. There's nothing, everything I'm talking about today is old, decades old, in some cases centuries old. But because we have these new sources of data, we're able to ask these questions in different ways or push them in different directions and generate new insights. I think also it's important to be realistic about what we're capable of doing, and there are lots and lots of problems, and there are lots of limitations, and there are things that we can imagine doing that we can't do, and things that we haven't even yet imagined doing. And so if I have time, and I usually run out of time, but I'll try to get at the end to sort of talking about some of the ideas, thoughts for kind of where we might go from now. And finally, I'll just say, this is very much an overview talk. I'll be presenting a bunch of different papers, and so I will not be going into details. I will be skipping lots of details. So if you're the sort of person who gets really frustrated when the speaker is skipping over details, please, bear with me. All of this is published stuff. I can share the papers with you. Happy to talk about it afterwards. But I apologize in advance for skimming over potentially important details. Okay, so let's start with this question of social contagion. I'm sure everyone here is familiar with at least some of this literature, which is pervasive both in economics and sociology and also in marketing, and these days in computer science and physics as well. And we have hundreds of, dozens of models of how things spread between people, ideas, behaviors, so on. And many, if not all of these models can trace their origins to earlier mathematical models of infectious diseases, how biological diseases spread among humans. And so what I would posit to you is that when we think about, we sort of abstract away from the details of these models for a moment, and what's driving a lot of them is this mental model of how things are spreading in some typically unobserved human population. And in the cases of mathematical epidemiology, this is exactly the model that is being formalized, where you have some individual who is initially infected, and in this case, so imagine the Ebola virus starting in West Africa a couple of years ago. It was literally the case that a single person gets infected with Ebola from some animal reservoir, and then that person infects a small number of probably his family members or immediate neighbors, and then each one of those people infects a few people, and each one of those people infects a few people. And over time, you see this branching process grow exponentially to infect a very large number of people over many, many generations of the disease. And so this is this sort of multi-step peer-to-peer branching process is very much what is represented in formal mathematical models of disease spreading and also social contagion, and also the kind of mental model that we have when we talk about things going viral on the internet. We have this notion of information spreading through social networks in this multi-generational way. The problem with that mental model is that historically the data that we have had doesn't look anything like that, right? So when we look at these sort of classic works of diffusion, so this is Everett Rogers' book, Diffusion of Innovations, which is one of the most cited books in all of social science, and then the Coleman, Katz, and Menzel work from Columbia, actually back in the 1950s, looking at the diffusion of tetracycline among doctors in the Midwest. What you see is on the x-axis is time, and on the y-axis is some cumulative number of adoptions over a whole population, right? So this is the type of data that people who study innovations have typically had over the years. And the claim is that if you see something that looks like this S-shaped curve, you can identify that there is some diffusion process or contagion process at work. And so the idea here is that, sure enough, here's this sort of initially infected person, and then as they infect a few people, it grows slowly, and then as it then kicks into this exponential growth phase and eventually asymptotes as it runs out of people to infect. So that's the claim, but there are some problems with evaluating contagion using these aggregate S-shaped curves. The first one is that there are lots of ways to generate S-shaped curves. It's not only the case that many of these models generate S-shaped curves, and so it doesn't really help you very much to disambiguate between models, but there are other processes that involve no contagion at all that can also generate S-shaped curves. So just assuming some sort of heterogeneity and propensity to adopt across the population can generate an S-shaped curve. Once you allow for marketing efforts, and almost everything social has some sort of marketing or media component to it, then you can also generate S-shaped curves. So it's very hard to, just because your model generates an S-shaped curve and your data is S-shaped doesn't mean that your model has generated your data. The second problem is that historically people who study diffusion only look at things that diffuse. Right? And this may seem obvious. Why would you look at things that don't diffuse? Why would you study uninteresting things? Why would you? But of course, this causes a big problem with the data that you're evaluating, because you're selecting on the dependent variable. If you only study successful things and you don't study unsuccessful things, then how can you predict what causes people to be successful? The same is true for I mean, this of course is a message that is lost upon all writers of business books in airports, but it's a problem anyway. So if we really want to understand the mechanisms by which things spread, we need data that satisfies two criteria. One is that it has to be at the individual level. We have to be able to see a thing spreading from one person to another person over many such spreading events. And secondly, we want to, in some sense, have a complete census of all the things that are trying to spread. And this is complicated, but we can get closer to that. So of course, this is an area in which the web has been very helpful, and there's now a sort of growing literature of work, mostly in computer science, that is exploiting these different sources of digital data. And so we can start to ask new questions like, well, how much diffusion is actually viral anyway? What do we mean by viral? Can we sort of be more precise about what a viral thing is? And can we predict it? I actually won't answer that question today. Okay, so I'll talk about a couple of papers. The first was a paper with Sharad Goyal and Dan Goldstein back at Yahoo Research. Back then it was sort of early days in terms of the data that was available, and we were really scrounging around to get anything that we could get our hands on. And so what we did was really reuse data from 6 projects that we had worked on, or that even our colleagues had worked on at Yahoo Research. And these were very diverse projects. We had a Facebook app that we had been using to study political attitudes. Dan had run an experiment, a psychology experiment, which several years earlier that was conducted online. We worked with some of our colleagues in the philanthropy group at Yahoo to do a sort of pay it forward giving campaign around the holiday season. Some colleagues of ours had built a synchronous video viewing app. There was a premium instant messaging app that Yahoo had released. So there's a bunch of different projects, some Twitter data. This is, of course, this before the deluge of everything on Twitter studies. So the point here, again, I'm skipping over details. The point is actually that these studies these data sets were very diverse, right? So every one of them is biased in particular ways. The sort of network, the population, the engagement mechanism, the diffusion mechanism, all of these were very sort of specific to the particular domain that we were studying. And so if you just looked at one of them, whatever conclusions that you reach could obviously be biased by any of those factors. So the claim here is that if we see similar patterns across all of these domains that have very different biases, then there's some robustness to the patterns. And in fact, we see tremendous consistency across these 6 domains. So each one of these little rows here shows you the 5 most common structural motifs that we see. And so let's just look at Twitter for a second, because everyone is familiar with Twitter. So what this little dot here means that 93% of the time somebody introduces, in this case, a shortened URL, back then it was a bit.ly URL, into Twitter, pointing to some content on the web, and nobody pays attention, right? So if you have that feeling sometimes, then you're not alone. Most people have the same experience. 5% of the time, one of your followers retweets your tweet. This shows you that 0.9% of the time, 2 of your followers retweet, 0.3% of the time, 3 of them retweet it, and 0.3% of the time, one of your followers retweets it, and then one of their followers who's not one of your followers retweets them. So this is starting to look a little bit like contagion, right? Notice that these numbers add up to about 99%. So 99% of everything that happens on Twitter looks like one of these very simple, not very viral looking motifs. And you see that pattern play out across all of these different domains. In fact, you have 6 domains and 5 potential motifs associated with each of them. So there's 30 potential structures that you might see. And we only see 7, which is these 5 and this one and this one. So and even the numbers look pretty similar. So there's tremendous consistency, and in fact you can aggregate up another level and say, let's put all the data together, and we can make the following claim that across all of these domains, about 90% of the time nothing happens. There is no subsequent adoptions. About 8% of the time each introduced item gets 1 additional adoption. 1% of the time it gets 2 adoptions, and 1% of the time is everything else, right? So everything you've ever heard of, every viral phenomenon, cat video, et cetera, is in this little blue bar here on the right. And you might say, well, that's interesting, but some of those things are extremely large, right? So, the Spanish flu, which happened about 100 years ago now, was a very rare event. It was one in, probably tens of thousands of flu epidemics that have happened throughout history, but it infected 1 billion people, right? Roughly a third of the Earth's population. So it would be silly to sort of ignore that and say, well, that's a rare event, we don't care about that, because it actually occupies, if you think about the total number of flu cases throughout history, quite a few of them were in that one event. So when we have these very, very skewed distributions of events, we care about these rare events. But what we can say here is something stronger, which is not only are most events small, but if we count up all the adoptions, almost all of them happen within 1 hop of the seed, right? So 99%, only 1% of adoptions are more than 1 degree from the originating node, and so only 1% of adoptions could sort of plausibly be called viral. So that's a much stronger statement than just that big events are rare. But of course you're saying, well, I'm still not convinced, because I know about this thing that, does anybody not know what this thing is? I have found one person who does not know about Gangnam Style. So this video has been viewed a couple of billion times. Google had to add a new digit to its counter on YouTube because it broke. So we know that these big things happen. We know that there are sometimes events that capture some sort of spirit and spread wildly, and many people see them. What we don't know is whether they're really viral, right? Because we also know that the Super Bowl is popular. 100 million people watch the Super Bowl every year, but nobody would say the Super Bowl is a viral phenomenon, right? It's a broadcast phenomenon. And so if we go back to our Twitter data from this earlier study, we can see that some of the biggest events look pretty broadcasty, right? So this is a single node in the middle, and then you get a lot of people at degree 1 retweeting, and then very little else happening, right? Which is a very different kind of structure from this mental model that we have of things spreading over many generations. And so it's possible that that's what's going on with Gangnam Style. And we know, for example, that Gangnam Style was featured on the front page of Yahoo. And 100 million people come to the front page of Yahoo every day. And so it's possible that a lot of those views were not really viral at all, but were driven by sort of traditional broadcast media. So how would we answer this question? Well, one way to do it is just to collect a lot more data. And so this is what we did, again, with Sharad Goyal, but this time also with Ashton Anderson and Jake Hoffman at Microsoft Research. And we took a year's worth of URLs from Twitter. So this is, roughly speaking, every video, every news story, every image, and every petition posted to Twitter over a 12-month period. So now this is, instead of 40 million URLs, we've got about over 1 billion URLs. And then we tried to address another criticism that people had of our earlier paper, which is that we just hadn't looked at interesting stuff. Right? And you might think, well, that's reasonable, because a lot of stuff that people post to Twitter, maybe it's not meant to be spread. Maybe there's no intent to spread. Right? So it's not really fair to count everything that gets posted to Twitter as something that's trying to spread. And so to alleviate that concern, we restricted this initial 1.4 billion observations only to URLs that got retweeted at least 100 times. Okay? So this is way more popular than anything that I showed you on the previous slide. In fact, these are very, very rare events. These happen only like 1 in 3,000 posts on Twitter gets 100 retweets. So you may never have had a post that gets 100 retweets on Twitter. And so we are, in that way, we reduce our initial population of over 1 billion to about 350,000. So we're a massive reduction in the amount of data that we have, but still a lot of observations of these rare events. And so this is kind of an interesting application of the big data principle that if you're studying rare events, it helps to have a very large population of events to start with. So now that we have this, this population of popular things, we can measure this property that we call structural virality, which is a little bit different from the normal notion of virality, which usually refers to some sort of parameter in a model that's telling you about how infectious, or how likely something is to get spread at each stage. This really is a way of quantifying the structure. So imagine that something is introduced, it gets retweeted a bunch of times, and it's sort of, as it does so, it's lighting up some path, some tree-like structure in the network. And then when it's done and all the retweeting has stopped, this structure is left over, like a sort of fossil or something. And now we can treat that structure as a network, and we can measure properties of it. And by definition, these are all acyclic branching networks. And so we can compute various properties of them, and a lot of them turn out to be equivalent, but the one that we're going to focus on here is just a very simple one, which is to compute the average shortest path length. So pick every pair of nodes, compute the path length between them. If it's a broadcast, like this structure here, then that number is going to be very close to 2, because everything except the central hub is 2 degrees of separation from everything else. And so that average asymptotically approaches 2 as the broadcasts become large. And then when we look at something that's very viral in this sense of multi-generational branching process, then the average shortest path length is going to be proportional to the depth of the tree, which is proportional to log n. So you get, for every one of these cascades, you get a number that's somewhere between 2 and log of n. And then you can compute that for every one of these 350,000 events, and you can ask questions about that distribution. So we're going to ask a couple of questions. First of all, what kind of diversity do we see when we look at all these different structures? Is there some sort of optimal spreading structure, right? If you sort of think about popular things, do they tend to be very viral? Do they, in this structural sense, do they tend to be very broadcasty? You could make up a story which would convince you of either direction, right? Or maybe it's some sort of optimal combination of the two, right? That there's some sort of a few broadcasts and then a lot of viral, or a little bit of viral, and a lot of broadcasts, right? That is sort of generates the most spreading. And then the second question we can ask is, how does this relationship change as things become more popular? So is there some sort of relationship between popularity and virality? So here's the, whatever you were guessing in your head. I should have asked you to write something down. Anyway, the result is that whatever you guessed, you're right. That we see basically everything, right? There is tremendous diversity. It's like a sort of zoo of structures out there on Twitter. And what this is showing you is 6 examples of cascades that are all about the same size, right? So they all have roughly the same popularity, but they have very different structures. So there's one at the top left here, which is the most broadcasty. Show this big black triangle is really a broadcast. It's just all the lines are printed on top of each other. So this is a single node here. It's, I think, CNN. This is some CNN story. And a bunch of people have retweeted, who follow CNN, have retweeted that story. And then there's a few little dribbles off the bottom here, but it's almost all the action is happening in that black triangle. And then you can see as you go from left to right and from top to bottom that the black triangle is becoming less and less dominant, and you're seeing more and more of what looks like viral spreading. So this is a New York Times obituary about some French freedom fighter who died a few years ago, who's lived into his 90s and had this incredible life. and escaped from the Nazis 3 times and all sorts of just amazing life story. But no one's ever heard of this guy, like just total nobody, but fascinating story. And so people were retweeting this thing. And so very different structure, but roughly the same popularity. And then underneath these structures, you can see what we're showing here is the sort of the data that you would have had back in the old days when you only got to count things over time. And you can see that that data is relatively uninformative, right? That a lot of these aggregate counts over time look very similar to each other. So this sort of the structure underlying is sort of completely obscured by both the time scale and the shape of the curve. So that's the first message, that diversity is really sort of hiding there under the hood. But the second message is a little bit less, well, I don't know if interesting is the right word, but less fun. And so this is showing now how structural diversity varies with popularity. And we've broken these box plots down into types of media. So we have petitions, news, stories, pictures, and videos. And the box plots show the solid black lines show the median, and the boxes are the interquartile range, and the dots show the full range of the data. So you can see from these long stringy things that's where the diversity is. That for any given size, you see examples of cascades that are all over the place, from very broadcasty to very viral. But the typical cascade is fairly close to the broadcasty end. And more, I think, interesting or less obvious is that continues to be true even as these cascades get bigger and bigger, right? So, and this is especially true for pictures and videos, where there's essentially zero correlation between size and structural virality. So what this means is that the size of the cascade is being driven by the size of the single largest broadcast in the cascade. So almost all the action has been driven by broadcast, and this is what we, at the time, called the Justin Bieber effect, because Justin Bieber was the most followed person on Twitter. Now it's Katy Perry, so I guess it's the Katy Perry effect. But these people have tens of millions. I don't know if Katy Perry has cracked 100 million yet, but she's sort of up there in the 80 million range. So this is sort of Super Bowl-like numbers in terms of coverage. So these are effectively, network broadcasters who just happen to be individual people. And when they retweet something, even if the retweet rate is extremely low, they get a lot of retweets. That's why I think pictures and videos show such a low correlation, because celebrities completely dominate the list of most followed people on Twitter, and celebrities generally talk about themselves, and so they're tweeting out pictures and videos. They're not really sort of delving into the details of healthcare policy. So you see a little more correlation in news, but it's actually still quite low. So there's sort of less of a broadcast effect in news. And petitions, interestingly, just more structurally viral in general, but again, very little relationship between popularity and virality. So what do we learn from studying this type of data? I think sort of the high-level lesson is that we have many theoretical models and thousands of papers that have been written about how things diffuse, and recently sort of imaginary diffusion processes spreading on imaginary networks, and it's really informative to actually go and look at some of this data, because what it has taught us is that we're really sort of looking in the wrong part of the parameter space. It's not that the models are necessarily wrong. In fact, we can replicate many of these features from relatively simple disease models. But a lot of the emphasis in the modeling literature has been around this, what's called the epidemic threshold, this phase transition that happens as you go from zero infectiousness and you pass some sort of critical value of the parameter, and the disease goes from dying out to spreading exponentially. And if you're an epidemiologist, you want to keep things below this epidemic threshold, and if you're a marketer, you want to get it above the epidemic threshold. But everybody is concerned about the conditions under which that govern that particular threshold. And what we're finding is that everything is well below that threshold, right? Nothing is spreading virally in that sense. There's this sort of constant dying out process. And this, actually, when you think about it, it makes a lot of sense that the world is just awash in people trying to get your attention all the time. And Twitter makes this completely evident. It's just overwhelming how much stuff has been thrown at you. And so just the competition for attention forces everything down into this sub-viral regime. And the only thing that can sort of compete with that stifling effect are these enormous hubs that can sort of push something out and keep it propagating for a while longer before eventually it peters out. This, for us, is suggestive of new directions to take the modeling, and if you're in the marketing world, it's also something to be cognizant of. And finally, it's I think a really relevant application of when the big part of big data actually matters. And there's a lot of, as you know, a lot of sort of hype around this label, and lots of claims are made that turn out to be not very useful. But I think when you're studying rare events, it really is necessary to have, in the case of this last study, 1 billion is not too many, right? It's about what you need to do this kind of study. And of course, if you redid this study today, you would get that many observations in a month, because the rate of growth of social media sites like Twitter is so tremendous. Okay, so I want to, as I'm running out of time, talk about this other topic, virtual labs, and of course this is another very old area. And we have, people have been doing lab experiments since probably the 1930s, and certainly in the 1960s there was a sort of golden age of studying organizations in labs, and this is the kind of setup that researchers would rig up. And there's lots of advantages of doing that. You get a lot of control. You can identify cause and effect more easily. But there's lots and lots of, there's a long laundry list of disadvantages, and I'm sure that you're familiar with all of them. But basically, the consequence of those limitations is that it's very difficult to generalize from the lab environment to the real world. And this is an old criticism, and it's quite valid. So good for testing particular theories, but very problematic for figuring out how those theories should apply in the real world, where inevitably lots of other things are going on. So one way to sort of view this graphically is if you sort of imagine the sort of design space of experiments along these 3 dimensions, each of which is probably multiple dimensions. One is the scale, how many people do you have in your experiment? Another is the duration, how long does it run for? And the third is sort of this realism, complexity of the experiment. And so the real world is kind of out here somewhere, large scale, long duration, high complexity. And the vast bulk of experiments that have ever been run in labs are sort of indistinguishable from the origin, right? Where you're like very small numbers, very short periods of time, typically less than an hour, and very stylized, simple games that are being played. So the challenge here is, can we use the web to sort of push out this red boundary and try to get closer to the real world? And so I'll try to give 3 quick examples. The first one is an old one. This is work that's done with Matt Selganic and Peter Dodds right here at Columbia over a decade ago. And we were interested in how social influence affects the dynamics of cultural markets. So people make decisions about what they like, but those decisions are influenced by what they think other people like. How does that affect the dynamics of the market? So you have the micro level question of individual decision making, and then all those individual decisions are aggregating up to the macro level of of distributions of success. And so we recruited, in this case, about 14,000 participants who were shown a page that looked like this, where they had 48 songs by bands they hadn't heard of. And in some cases, they just saw the names of the bands and the songs. And in other cases, they were randomly assigned to see how many times those songs had been downloaded by people ahead of them. So there's a weak social influence signal there. And what we were able to show experimentally is that when people know what other people like, popular songs become unpopular, popular songs become more popular, unpopular songs become less popular, so the distribution of success becomes more unequal, but at the same time, the songs that become most popular become increasingly hard to predict. And we were able to show that by creating multiple copies of this world and comparing the distribution of and the ranking of popularity of songs across these different worlds. So this helps us to understand, what the mechanism is that's driving unpredictability. But it also shows another interesting phenomenon that sort of blends the psychology and the economics of markets, where economists are focused on markets and they're revealing of preferences. Psychologists are much more interested in how markets, or in how circumstances construct preferences. And what we find here is an example of where the market itself is not just revealing preferences, but is also constructing them at the same time. And so in that sense, there's no way to get rid of this unpredictability. It's something that's baked into the dynamics of the aggregation process. So this was sort of scientifically a very interesting result for us, but it also demonstrated this important methodological point, which was that you can now, there's not that many undergraduates at Columbia. There's no way that we could have run this experiment in a physical lab. And you have to have that many people to do this experiment, right? That each one of these worlds that we created had a couple of thousand people in it, and you needed that number because you had to aggregate over so many individual level decisions. Okay. So the second dimension that I wanted to mention is this question of realism, that the Music Lab experiment was interesting in terms of scale, and you can see new things by simply jacking up N in the experiment. But it's a very simple, you're clicking on a song and saying, I want to download this song. And that's sort of a fairly impoverished measure, even of popularity of music. It doesn't tell you very much about how groups of people do other things that we're more interested in. And so this is a question we've been grappling with for years about how to study problem solving in groups of people where the problems are not completely trivial and artificial. So we were looking for a task that was sort of real enough that it looked like something that happened in the real world, but was simple enough that we could put it into a lab setting and actually study it in a controlled environment. And so a few years ago, I met this guy, Patrick Meyer, who runs this organization called the Standby Task Force. And this was started in 2010 during the Haiti earthquake, or right after the Haiti earthquake. And he was a graduate student at Harvard at the time, and he was sitting in his dorm room wondering what he could do. And he had this insight that, in the rubble of Port-au-Prince, where the relief agencies were having a tremendous amount of trouble figuring out how to allocate their resources because there was no information about where people were or what their state was, that there was actually a lot of information, but it was being produced in this noisy, unstructured way via social media. People were sort of tweeting things, they were posting things online, and so he got together a group of volunteers and he sifted through this information and pulled out those sort of instances where somebody had said something quite specific about their state or about some damage that had occurred, and he put it all on a map, and that's what's called a crisis map. And so crisis mapping is now this thing. There's a whole community of people around the world who do crisis mapping, and this standby task force has deployed a number of times over the years mostly in natural disasters, but also during the Libya crisis. And so this is something that the UN finds pretty helpful. So this is sort of a real-world task that has real-world consequences, but it's a natively online activity. So this is like a bunch of people are recruited on the fly. They are, interacting via various web tools, and they're creating a digital map, and that's which can be evaluated for its accuracy. So this sounds like something we might do in a lab, right? And that's exactly what we did. And this is work here with Andrew Mao, who just finished his postdoc at Microsoft Research, who built this incredible app that I will show you. Let's see. And also Winter Mason and Sid Suri from Facebook and Microsoft Research. And so this is crisis mapping in a lab. And on the left-hand side, you can see all of these little boxes scrolling down. Those are real tweets that were produced by people in the Philippines in December 2012 when Typhoon Pablo rolled through and caused a tremendous amount of damage. And this is data that we got from Patrick at the Standby Task Force. This is real data that was really used in a real deployment by the Standby Task Force back in 2012. And it's about 1,500 of these tweets, and most of them are not saying anything very interesting. They're just talking about this typhoon, or they're all, in some sense or another, about the typhoon, but they don't have any useful information. But a small minority of them are very specific and mention or have pictures of washed out roads or bridges, damaged houses, displaced people, events that the UN OCHA, the Office for Coordinating Humanitarian Affairs, is interested in. And so what these guys are doing, and this is a bunch of people recruited off Amazon's Mechanical Turk, they are doing exactly what the Standby Task Force was doing, which is trying to find those relevant tweets, documenting them in this little spreadsheet here, geolocating them, which is tricky because many of them are not geotagged. So you have to do some sort of sleuthing to figure out where this village is that they're talking about. And they're putting them on this map. And so once we have this map, we can evaluate it for accuracy. So we did this not once, but dozens of times with different numbers of Turkers. And so the first kind of face validity question is, can they do this? And it wasn't obvious to us that in 1 hour, a bunch of random people could even do this, right? Because when you start, it's actually quite difficult. But Turkers are amazingly good at just focusing on the task that you give them, and they take it very, very seriously. And they were able to produce maps that were surprisingly similar, and in some cases, as good as the map that was produced on the left here by the Standby Task Force over a period of 24 hours. So the question we were interested in is, how many people should you recruit? Like, what should be the group size? And there's all kinds of conflicting theories about the relationship between group size and performance. So in one set of theories, individual performance goes down with group size because of free riding, or as the psychologists call it, social loafing. And in fact, we see that. We see that effort is going down. Individual effort is going down quite substantially as a function of group size. The more people there are to do things, the less pressure you feel to do them yourself. So maybe you should just recruit a bunch of individual people and have them work on their own. But then they can't talk to each other, right? And then they can't help each other, and they can't correct each other's mistakes. And so you might think that that collaboration would help. And in fact, we also see that, so that as the group size increases, we increasingly see people working on the same events together and checking each other's work and updating it and making suggestions and deciding that that event that you're reporting is actually the same thing that I'm working on. We should merge these two reports because it's redundant. And so there's a lot of that kind of activity going on. And what we see here is this trade-off between the two, and this blue line here, where the performance, the accuracy of these maps is at first, this blue line represents what we call synthetic teams, where you take individual maps and you combine them. So this is sort of giving the individuals the best chance at competing with actual groups. And you can see that the blue line is at least as good as these black dots, which is the raw data, up until about groups of size 8. And then the inability of individuals to talk to each other and to correct each other's errors outweighs the slacking off effect. And the larger groups actually do better. And in fact, the largest groups do about as well as this red line here, which is the real performance of the standby task force. So the message is that collaboration, in this case at least, trumps free riding with increasing group size. So finally, I want to talk about duration. And here we're going to study a classical game. This is no attempt to be realistic here. This is a game that has been studied many times in lab environments. This finitely repeated prisoner's dilemma. And so the basic unit of the game is 2 people playing a 10-round game of prisoner's dilemma with this payoff matrix. And what we see here is the same thing that people have seen for decades, which is that individuals start off cooperating, and then as they get to the end of the game, one of them tries to take advantage of the other by defecting, and then the other one retaliates, and then we end up in mutual defection for the rest of the game. So the question that we're interested in is what happens if they play this game again? You assign them to a new partner, and they play the game again, and then you assign them to a new partner, and they play the game again, and they just play and play and play and play. What will happen? And one theory that was advanced by Krebs back in 1980 is this notion of rational altruism, that really the players are rational, but they think that other people might not be rational, and so they think, if you're going to cooperate, it's in my interest to cooperate. But if you start running into people who are just like you, right, and they take advantage of you, then if somebody defects on you in round 8, then the next game you're going to be smart and you're going to defect in round 8. But if you run into somebody who wasn't going to defect in round 8, now they become disillusioned and they start defecting in round 8. And then people start defecting in round 7, and then people start defecting in round 6, and you see this kind of unraveling, well, the theory is that you will see this unraveling, and eventually if you play this thing for long enough, you'll end up back at the Nash equilibrium where nobody is cooperating at all. So people have tried to study this unraveling behavior in lab experiments, and the most recent case is Matt Embry and colleagues at NYU did a very careful study a few years ago, and they ran about 20 experiments over the course of an hour, and they saw the unraveling begin. And so they hypothesized that this will continue and eventually cooperation will be extinguished, but it will take a long time, and it's far too long to sit around and study in a physical lab. So this is, of course, perfect for us. We want to try to do this online. And so we did essentially exactly the same experiment as Embry et al. And others before them, except that instead of running it for a single hour, we brought the same people, the same 100 Turkers, roughly 100 Turkers, back every day for 20 consecutive weekdays over the course of a month. And so what that looks like is this is one game, and then we randomly reassign people, and they play 20 games, so that's what one session looks like, and that's what 20 sessions look like. So there's 4,000 rounds of Prisoner's Dilemma there. You might think, who can play 4,000 rounds of Prisoner's Dilemma? So boring. Once again, like, Turkers are amazing. Like, they really, I mean, and this is, by the way, this is true of Prisoner's Dilemma experiments in general, that people get really into this, and they get very personal about it, and they get really upset when other people, there's one guy who, like, obviously took, like, the first semester of economics, of microecon, and learned that, like, the Nash equilibrium was to defect on all rounds, but didn't take the second semester where you learn that nobody actually plays like that. And he played all defect the entire month. And everyone hated this guy. I mean, they all wrote about it, like, there's one jerk, he won't. So they really get very into this, and he did very badly, by the way. It's a terrible strategy, never do that. So what did we learn? Well, really, not what we expected, right? We were very convinced that this unraveling would happen, and that's what we were hypothesizing. And we had all kinds of ideas for what to do after cooperation had completely unraveled. And for the first 7 days, that's what it looked like was happening, that things were this is the last round, this is the second last round, this is round 8, and then round 1. And you can see that cooperation is declining quite precipitously in these latest rounds. But after about 7 days, it stops. And it just sort of sits there for the rest of the experiment. And we kept waiting and waiting and waiting. And eventually, we played this thing for a whole month, and it never went down. So then we were puzzled what was going on. And we looked very carefully at the strategies that all of these people were playing. And we found that there were roughly 2 groups of people. There's sort of about 60% of them were playing like the Krebs paper suggested. They were rational altruists. They were forming a hypothesis about the distribution of types in the population, and they were roughly playing some sort of best response to that distribution of types. And as a result, they were starting to unravel. And so T9 means that I cooperate until round 9, and then I defect on round 9. T8 means I defect on round 8. And so you can see that everyone's sort of starting off cooperating the whole way, and then they're kind of gradually unraveling. But this second group of about 40% of the people at the top don't do that. They just don't. They don't do anything. They say, I'm going to cooperate unless someone defects on me, and they just play that. They don't update. It's like they don't learn. They get annoyed, and they report this in the exit surveys. But for various reasons, they don't unravel. And so we call these people resilient cooperators. And so that has 2 effects. First of all, they boost cooperation. But the other more interesting effect is they stop the unraveling. Because the unravelers, the rational people, are roughly trying to balance, they learn that about 40% of the population are not going to defect unless they do. And so they get to a point of the unraveling where it's better for them to not unravel any further. And so these resilient cooperators are able to keep cooperation pretty stable throughout the entire experiment. And interestingly, they pay a price for this, right? So their payoff, their average payoff, is significantly lower than the people who are not resilient cooperators. But they are willing to do this, either out of principle or sort of enlightened long-term self-interest, where they think, well, if we start, and they actually would say this, I mean, it's very interesting, the people, they've clearly thought about what their strategies are, and some of them would say, well, if I start unraveling, then everyone else will start doing it, and then we'll all be worse off, which is true. And so they're happy, well, not happy, but they're willing to pay this penalty in order to benefit the collective. So a fascinating result that just could not have seen if you couldn't run the experiment. You had to run the experiment for many days to even see this behavior. It just, it's so a novel result that illustrates the benefit of running things for a long time. So lots of interesting things. Thank you.
Thank you. We have a few questions, that's okay. We have a mic down there. Okay, great. Thanks very much, Duncan. I was watching this. For those of us who are academics, we want people to pay attention to us. I mean, he started off, it was kind of depressing, right? Nobody really cares about what we do. Nobody reads it. But the end part was really good. That is to say, we have pro-social people in the economy that are going to save us. Right. And I hope all you guys are obviously very pro-social and help save the world. So what I'll do is maybe we'll open up for a few questions for Duncan. Anybody have questions? Yeah. And you can actually field the questions.
Sure. Yes, thank you.
So I'm just wondering who the resilient cooperators are. Are they men? Are they women? Are they young? Are they old?
Good question. They don't fall into any obvious demographic category. They're not predominantly male or female, and age is trickier because it's all self-declared. But yeah, we don't see any obvious pattern. Yeah, that they have different motivations for being how they are. Some of them seem altruistic. They seem to have pro-social motivations. They care about other people's payoffs. Others seem to be responding to norms, so they would sort of say, well, it's the right thing to do, and some of them would even say, well, I tried defecting, but then I felt guilty, and so I went back to cooperating. And others seem to have this kind of enlightened self-interest perspective of this is something, this is actually good for me in a certain way, so I'm going to keep doing it. So, our experiment wasn't designed to try to identify between these different strategies, but I think, in future work that would be interesting to see if we could connect this sort of behavior to, other attributes, whether psychometric or demographic or even sort of how people play other types of games. Right? Yes. In the middle there.
So for these resilient cooperators, do you have any suggestions or thoughts about if we actually ratcheted up the costs that they had to bear from continuing to cooperate?
Yeah.
Whether or not this cooperation would then decay more rapidly?
I suspect the answer is yes, it would. And in our original design, we wanted to split the population and have two different sets of payoffs. One which was relatively favorable to cooperation, which was this set of payoffs, and another which was relatively challenging to cooperation. But we were so concerned about attrition in the experiment because we'd never run an experiment using Turkers for more than an hour. And so we were so concerned that over the course of a month we'd lose too many people. And so we decided to just pick one set of parameters and use all of our population. But then we got very little attrition, and so in retrospect, we could have done, we could have looked at the two sets of payoffs, and I think my guess is that you would definitely see more unraveling, but not total unraveling, right? That at least this is our hypothesis that these resilient cooperators are really a type, and you would probably peel some of them off if you made it more costly for them, but there would still be sort of some fraction of the population that would be behaving that way, and they would still have the same kind of anchoring effect. So anyway, we did some modeling, some simulation modeling, which has generated the new hypothesis about what we should expect as we vary the fraction of resilient cooperators, and that would be, I think, a fascinating follow-up experiment to do, but we haven't done it. Thanks.
So I would be interested in your take on how, like, the interaction of natural agents such as the Turkers with artificial agents such as bots would basically influence this, right? So I guess like we see more and more of these interactions, and I would also think that this justification of basically, I want to cooperate because I want to induce other people to cooperate might sort of break down if I know that a part of them I know are sort of bots that will always defect, for example.
Yep.
And sort of like, just stepping back from the specific question, do you have like a take on, because I'm sort of like thinking more and more about things where, specific things in organizations and institutions, we sort of like rely more and more on artificial intelligence to solve tasks that typically were done by humans. And so the interaction between natural agents and these like artificial agents might sort of,
Yeah, so I would say two things about that. One is, in some earlier work, we did actually introduce bots into a networked version of a public goods game, and sure enough, when you have very cooperative bots, they have a small positive effect on their partners. When you have an uncooperative bot, it has a much larger negative effect so it's an asymmetry between positive and negative. In that case, the people didn't know they were playing with bots, right? So they just assumed that everyone was a human. So you can, so the first answer is you can certainly, it seems you certainly can tweak cooperation levels to some extent by inserting cooperative or uncooperative bots into the mix. But then the second question, which we haven't looked at, is how that is moderated by knowing that they're bots, right? But I think Selton and Stocker looked at this back in the 80s and didn't find, I think people are sort of less offended by a bot defecting than by a human defecting. So I'm sure there's some very interesting psychology here, which I don't think has been worked out yet. But so that would be I think that's a really important modifying effect, is whether or not people know that they're bots, and whether that makes them maybe they don't like that because they don't like playing with bots, or they don't like the fact that the bot can't be persuaded, or maybe they think it's okay because it's just a machine, and so they don't take it personally. And you could imagine all of these things are possible. And I think, again, this is an example where these virtual lab experiments, in theory at least, have some advantages that you really want to test a lot of different variations. And so the sort of ability to run experiments quickly and relatively costlessly, not costlessly, but cheaply, should help us do that.
One more question.
I was wondering what the beliefs are that they have about the population. Okay, thank you. So what the beliefs are that they have about the population. So do they know how many people are involved? So how many people they are playing? And is this a perfect stranger matching, so that I know I will only play once with the same person?
So it is perfect strangers. There's no identifiers. No one is labeled, right? So you don't know that you've played this particular person before, and you don't know anything about their reputation. So there's no reputation, and there's no memory. I mean, there's no.
But then it's so if there are no labels and so on. So do they explicitly know it's a stranger matching? So I will only play with you once. And do they know how large is the population?
No, so we don't tell them how big the population is, but they could figure it out. If they were really thinking about it, they would know roughly how many people were involved, and they would probably assume that they were the same people, and they could then assume that they would encounter the same person repeatedly. But let's see. So there was 2 groups of 50, and you're playing 20 games per day, so you might expect to encounter the same person roughly every 3 days, right? So that it's conceivable that knowledge further encourage them to behave cooperatively. Yes, but of course, exactly. You never know when you're actually playing that person again. So, yes.
But you can control for that. If you would make explicit that it's a stranger matching, so you will just play with a person once. That would be interesting.
You could yes, you could do that if you had
a
larger population. Yeah.
Okay, great. Well, thank you so much. I think in particular, Duncan just had a baby boy last week. So in addition to thank you for this talk, let's also congratulate him on the new addition to his family. Thank you.